I guess that you can see my screen. Can you please confirm?
I see your slides in PowerPoint right now. Yep, and now they're being presented.
Excellent. Okay. So as I said earlier by Sarah, I will be talking about the normal database system, but mostly focusing on a digital sample freezing platform, which I believe is closer to the interests of BP for NTA colleagues. The contents of my presentation are the following. In the beginning, I will describe the existing infrastructure. I will talk about the database management system and the various elements, the FAIR data catalog, the FAIR API and deep search, then instant search, and say a few words about the DSFP services. Then I will give you an overview of the current enrichment of the database, and I will discuss the future plans, the immediate future plans. So the normal database system, as you probably are aware, you can find it in the Normal Network website. Normal Association is a network of reference laboratories in Europe mainly, but also beyond Europe. And we have decided to create our database system and collect information about contaminants of emerging concern, which are chemicals that are currently not included in monitoring and routine studies, monitoring campaigns. It consists of several modules, as you can see from the screenshot. One of them is the digital sample freezing platform, which, as it says in the slide, is a database for digital archivation of high-resolution mass spectrometric data. DSFP, together with Mass Bank Europe, are the two main non-target screening databases of the Norman database system. All started back in 2019 as a follow-up activity of Norman News, which was a small-scale testing of digital freezing. The idea was pretty straightforward. There are many laboratories in Europe and also elsewhere. They have different analytical instrumentation, high-resolution mass spectrometry devices, and they are producing data, and the data can be brought in a server, and then they can be processed using a non-target screening workflow that is standardized and that produces reliably component lists, as we call them. So we have a workflow, a standardized workflow. We create the component list, we attach the retention time index for liquid chromatography or retention index for gas chromatography, and then we end up to pre-programmed Excel files. We call them data collection template, and data collection templates together with the MZML files, which are the raw HRMS data, end up to a server, and then there is a web interface through which the users can interact and can perform retrospective suspect screening, and more specifically wide scope retrospective suspect screening, meaning screening of thousands of contaminants in the digitally archived data. And they can do through information that exists in another module, Norman SUSDAT. And in case of a known substance, we know the mass of interest. We have the retention time index telling us, giving us information about the plausibility of the retention time. And then we have the qualifier ions. And this would give us enough information both to researchers and also to policymakers. This has been communicated in a scientific publication in Trends in Analytical Chemistry in 2019. From then, things have changed. The Norman Association has decided that DSFP is a strategic tool for non-target screening and communicating NTS to the regulators, and has has given some funds to redesign and recreate DSFP. So right now, the existing infrastructure and an overview is what you see on the slide. The heart of the system is what we call the DSFP data management system, is a place where the data provider, who is an analytical chemist working in an analytical laboratory, acts as a data provider, And this system is supported by a relational database, Postgres database, and a file storage system for storing all the data. The data management system is interfaced by a FAIR data API that gives us the opportunity to retrieve information and create a FAIR data catalog with all the collections and the samples that have been contributed in the data management system, but also the possibility to perform deep search, which means searching of contaminants of emerging concern in the data, but also something new that we call instant search, which contains all the detections, and we aim to impact the policymakers through instant search. This system is supported by DSFP services, which are in reality some scripts that are doing some processes. And these scripts are connected to a data index cluster, which gives input to instant search and also to the FAIR data API. So this part of the platform is handled mainly by data scientists, software engineers, and non-target screening experts. You can find the platform in the following in the URL that you see on the bottom of the slide. It is also accessible through the Norman database system as well. Let's move on and see piece by piece, part by part, how it actually looks like. So the first is the data management system, and the main panel looks like this. It helps the laboratory assistants and the laboratory people who probably control an analytical instrumentation to input to register laboratories, to register instruments, instrument setups, and then once an instrument setup is registered in the system, someone can create collections, and each collection is populated with samples. This is done because in some cases we have complex organizational structure, and maybe one university, let's say, or one department consists of more than one labs, and in many cases there are many more instruments. The labs and the instruments are resources that are available for all the members of a specific organization. In this case, we minimize data handling, and also we avoid errors. In the next slide, I have simply a screenshot on how to input an instrumental setup. Here, in this case, in this specific example, we have put as an instrument a Maxis Qt purchased by Brooker. And this is an LC HRMS instrument, and we set up some basic information, set up alias, some remarks, the ionization type, positive or negative electrosphere ionization, and then there is a stepwise procedure to input the separation settings. So what happens in liquid chromatography or in gas chromatography if it was a gas chromatography instrument, what happens with the detection settings. For example, it is a CID fragmentation or HCD fragmentation. Then we have some ionization specific settings. This is the retention time index of the RT calibrants. And finally, we have some spiked compounds and their area, which helps us a lot to semi-quantify the detected signals. And I put as an example also the collections of this specific user. This specific user has contributed 3 collections. And you see that the first one is Victoria Lake sediments from Victoria Lake in Africa. There are 82 samples contributed. So someone can add a new collection. A new collection in this case, it means maybe is more closer to a project. For example, we conduct a monitoring campaign, the Joint Danube Survey. So this can be a collection. And once someone clicks on the 82 samples, he or she is redirected to this page. and you can add samples, as many samples as you want. By clicking on Add Samples, you will be redirected in the screen. You have to specify the sample type. You need to give a short but precise and descriptive name for your contribution. The sampling date is also important, the analysis date, the pre-concentration, which is very useful for semi-quantification purposes. And then someone needs to declare the instrument setup that has been used, and also provide input about the monitoring scale, the precision of the coordinates, and also latitude and longitude, which enables us to do some spatial distribution analysis. This is pretty basic metadata, and I believe that for reusing purposes, this is very important to be given. Of course, these fields some of them can be left empty, but we highly motivate our contributors to input this information. Then we have some matrix-specific metadata. This has been separated in environmental monitoring, human biomonitoring, and foodomics. And here you see the breakdown of the matrices for environmental monitoring. And more specifically, we have selected surface water. So we collect metadata, matrix-specific metadata, for every matrix. This again is very useful when we hypothesize that we want to analyze samples after 5 years. So this is definitely a useful piece of information. And at the end, we upload the files. And files, all data acquisition data files are allowed. Full scans, data-dependent, data-independent, SWAF, inclusion lists. You can upload the files in the third step. So this is what the lab manager sees, and this is how the lab manager manages the assets. So once a collection is created, once a collection is populated with samples, then the FAIR data API is updated and gives input to the FAIR data catalog. There is a lot of insisting on the capital FAIR is a way to manage research data that are findable, accessible, interoperable, and reusable. So in European Union, we place a lot of, and the funders place a lot of emphasis. So the FAIR data catalog looks like this, what you see in front of you. It is actually a short description, short name of the collection. In this case, is the Norman semi-quantification trial that has been created by has been run in Norman by Stockholm University and University of Athens. Every collection receives a unique global persistent identifier, a DOI. This means that it can be cited in the future. And then you see the description, and below that you see the license, which is very important because it sets the reuse instructions and how someone can reuse the data, and also who uploaded, who are the authors, who are the contributors, a lot of information. Then we have the files. Here you can download the files, a map where you can visualize geographically where are the samples, and then we have the data API. And this data API is the place where we can programmatically perform deep search. So the FAIR data API gives us the opportunity to do searching of contaminants in the files. How this is done? There is this API is well documented. There is an introduction. Then the API explains to the user how you can get the sample metadata, the instrument metadata, the instrument setup metadata, and where are the files and how someone can download them. This is the basic information. And then it helps the user step by step to create a script so that he or she can search for specific contaminants. In this case, we have selected sulfonamide, sulfaguanidine, we add this substance to search query, and it gives us in section 322 the script. The script can be a cell, can be executed in the command line, or it can be written. We can use a programming language. In this case, I have highlighted R because many of us are using R for our day-to-day jobs. So all the user has to do is to copy this specific chunk of code and create and paste it in RStudio in this specific case. So what these lines of code say, it says that there is a service in the domain server.normal-data.eu/service/batch detailed. Encoding is JSON. There is a payload. This payload is all the information that the server needs. For example, in this case, we are searching collection 1233 for a substance that is called tramadol, which has a retention time index of this much, has a MZ of this much, molecular formula this one, and all the information. It practically gives all the necessary information, and then we ask the server, we use the service. This will give us a JSON. A JSON is like an Excel file, but is a more high-level, high-structure representation structure. So we are using then a library called JSON-Lite, and we convert the JSON using a function from JSON, and we store it, and then we convert it to a data frame, and then we can see. In this specific case, for tramadol in this specific collection, the output looks like this. So you see there are 40 entries, 40 rows, 40 samples actually. And here you see if the substance is detected and how many matches we have. And also gives us the evidence we have in our hands that this is tramadol. For example, you see an isotopic fit score, a retention, how well retention time index is matching, how well is accuracy, how well is the fragmentation pattern, how well is matching the fragmentation pattern. This is the information we are getting, and this is an example of a JSON, of a detection JSON, as we call it. Again, the way it is structured, it gives us some information about the compound, some information about the collection and the sample, and then it gives us the matches and the scores, the evidence we have that this is the specific compound. When a curly bracket starts, then a curly bracket ends, and then we have the next sample. So this can be a pretty long text file. All the formats, because it is a fair requirement to use the declared data schema, we declare the data schemas in the main website. In the landing page, if someone presses the data schema, there you see all the definition of the schemas that we are following. We are using schemas for describing the collection, the samples, the compounds, the detections, the instrument setups, and the organization. I will not enter in details here, but all the information is available in the website. And this here is another script that does search of sulfamethoxazole, another substance, but in this case, it does it for many collections. So it goes in many collections, having these specific IDs you see here, and it gets the chemical occurrence of this substance. And the output, then there is a for loop. So we are calling the service many times, and we save the output in a list object named output. If someone is knowledgeable of using R, then this output can be used in many applications, let's say. For those who are not familiar, with R, we have created under search on the main bar menu, deep search, and there intuitively you can select a collection, filter by methods, select the substances of interest, and search. What is very critical and what I want to highlight is a recent development is a better communication in the confidence of the identifications. In this specific case, we have a substance, and as you see, we have a mass score, a retention time index score, an isotopic fit score, a fragment score. So we have calculated some scores, and we have communicated in scientific literature this scientific publication where we showed the researchers a better way, a more efficient way to communicate how confident they are with their identifications. So we have taken the 5 levels, the 5 well-established levels of identification, at least in the environmental chemistry, and we have given a more quantitative measure. And here you see the ranges of what we call identification point score. And this score can be calculated either automatically, so a computer calculates the IP score, or someone can do it manually using the scheme that you can see on the right side. I will not go in details, but I highly recommend you to read the respective scientific publication. Okay, so we have the infrastructure. The lab managers can put the data there. The data become fair because they are accessible, interoperable, reusable, findable, because the results are also indexed in search engines like Google. But a new need is the instant search. And instant search is like when someone performs deep search, the results are stored in a separate index, in a separate database. And then the policymaker, who is interested to get results as fast as possible, he uses instant search. And this gives results within 2 or 3 seconds. How this looks like, on top there is a search, instant search. You select the collection. In this case, we have chosen European dust. We selected a list that contains 1,121 substances. We press search, and automatically it gives us the results. And then the results can be visualized in heat maps. Like in this specific case, we have gotten some substances. We selected some collections, and this is the output. Here, what you see 252,000 data points. So this picture here has this many pixels. And the color gives us a sense of the concentration level. And here a regulator can decide if a substance is persistent, if a substance passes to the groundwater, and can have many valuable conclusions for their evaluation. Final word on the DSFP services. We have numerous DSFP services, and you and everyone can create services. The way this is done is pretty straightforward, but it requires some deep knowledge of programming. No matter what you do, you will create a script that is written in Python, in R, in JavaScript, in a language. This code most probably has some dependencies. This means the script to run, it depends on other packages. So what you have to do is create a Docker file that instructs the installation of all these dependencies. Then this Docker, your code and your virtual environment can be uploaded to a container register and deployed on the cloud as a function. A famous service for doing that is the AWS Lambda service. Once this is done, then the user or the website or anybody having an appropriate key, having an appropriate authentication, and using an API can go and use the DSFP services, and the DSFP services have an output, some data. In this case, we have JSON data as output, and this JSON data is indexed, is stored in specific databases having some technology. For example, Elasticsearch, MongoDB, and there are other commercial and non-commercial databases. So this is pretty much everything regarding the architecture of DSFP and how it looks like. Now let's move on to the second part, which is the enrichment of the database. Currently, we have many projects, many EU-funded projects contributing data to DSFP, NTS data to DSFP. Just to name a few, here you see some of them. Life Apex that gives a lot of NTS data from top predators and their prey. Terrachem that similarly gives information on top predators and their prey. We have many pan-European monitoring campaigns taking place in major European rivers, Dniester, Dnieper, Elbe, Joint Danube Survey. And there are many other projects like Solutions, Aquality, Answer, Inquire, Clean Water. All of these are contributors. And here you see the map. And if we have a sample from a specific region, it is not anymore blank. So we have achieved a very relatively good spatial distribution coverage from Europe. However, this is not valid for all the other continents, especially in the United States. In America, in Northern America, is almost black. In Southern America, you see we have few samples here and there. In Antarctica, few. In Africa, very little. So there is a lot of space of improvement here. And even in Europe, there is a lot of space for improvement because we have many matrices to cover, and we don't cover all of them in a sufficient manner. This is a breakdown of the number of data by country. Here you see in the first places, Turkey, Spain, Greece, Germany, Ukraine, and other countries following. And we have, for some of them, little, very low amount of samples. And this is how it looks based on matrix. So as you can see, we have many wastewater samples. This is followed by many biota samples, many surface water samples, but we lag very much behind in groundwater, in soil, in sediment, in suspended particulate matter, air, and sludge. And then the future plans. And the future plans are two main ones and many other secondary plans. The first one is to make the normal non-target screening prioritization framework to bring it in life. There was in 2023 a scientific publication by the working group leader of Working Group 1, Prioritization of Contaminants, Valeria Doulio in Environmental Sciences Europe, where together many researchers we were explaining how we can have substances and how we allocate them in action categories. And then once we allocate them in action categories based on the research gap, then we perform ranking based on indicators, hazard, exposure, and risk indicators. And we have done this in the past for target screening. And here you can see that we have a list of substances. We are searching our target databases, if it is sufficiently monitored, if the LOQ is lower or higher than PNEC, which means is our method sensitive enough? And then do we have an experimental or predicted PNEC? And we end up in categories. For example, category 5 means improve ecotoxicological data and monitoring. Or category 4 means improve analytical performance. So we did the same, we followed the same logic, but for NTS data, for data that contain occurrence of substances that we have never done target screening. So we can go to DSFP, search for the occurrence, aggregate data information, and allocate in categories. Here, a key question in this scheme is the identification score above a specific threshold? It means, do we have a reliable identification or not? So this has been successfully applied in a pan-European effluent wastewater treatment campaign for 65,000 substances. And we have published this, and we want this to make it as an application in the NDS. Then another major future goal is to use PARC, to synergize with PARC. PARC is a European project, Partnership for Assessment of Risk of Chemicals, with 400 million euro as budget, with a very high amount of budget. And there we are creating the early warning system for chemicals in Europe. How we do that? We have the early component, so we get input from various sources of information. So we get early signals. The early signals are translated in specific chemical structures. Then the chemical structures, we retrieve exposure and effect data. And then we have a specific decision system that gives us an alert or not an alert. So DSFP contributes in exposure. So this is a major future goal that we have. And then we have many other minor but also important goals. I have listed here 10, but in reality we have far more. First one is to screen and index all the collections that exist in DSFP, and right now we have 75 of them. We want to create a statistical plugin, kind like MetaboAnalyst integrated in DSFP. We want to create a new API mechanism for predicting all the necessary properties for screening new substances. Right now, this has not been automatized to a level that we need. We are already testing 4D HRMS data, ion mobility HRMS data. We want to do it for all vendors and update what we call a cookbook, which is a list of instructions actually on how to convert your data. We investigate possibilities with integration with MassBank. We want to prepare, and we are preparing a manuscript on the new technologies that have been used to upscale and re-engineer DSFP. We need to make the contribution system easier. But also we need a critical amount of data, because the regulators, they need a lot of data to have enough and convincing evidence that the chemical is hazardous. And this is where we need the help of the scientific community, of course. And we believe that the platform will help and will stimulate cooperation among researchers and non-target screening experts. And finally, what we want is to create a product that is ready to be used for any scientific projects. This is valid not only for DSFP, but also for all the Norman database system modules. Okay, and with that, I would like to thank you very much for your attention, and I open the floor for questions.